Great. Oh, well, thank you so much. Yeah, so... Okay. Well, perhaps I'll start. So this is a talk on piecewise linear maps. And piecewise linear maps were a major part of the summer school we've had the last 10 days. Piecewise maps arise in diverse applications, as we'll see. So today I wanted to talk about two aspects. First of all, fixed points on switching manifolds, and secondly, shrinking points of mode locking regions, and I'll say what all this means shortly. Okay, so first of all, we're going to consider this map. So for those of you who are at the summer school, you'll recognize this as the two-dimensional border collision normal form, but without the constant term. So for those of you who weren't there, that this is a map on the plane. So X, Y. So what this does is, so for any point xy, just any point, the function takes us to another point, f of xy, and then we can keep iterating the map to get f squared of xy and so on. And we're interested in the behavior of the map as we keep iterating. The map is continuous, but it's non-differentiable on x equals 0. So there's x equals 0. That the map has 4 parameters. There they are. That these 4 parameters can take any real value. Yep. Okay, so that the origin is a fixed point of this map. Here's the origin. And the most basic question we could ask is the origin stable? So by that I mean, do iterates converge to the origin for all nearby initial points? And so for smooth maps, we just look at the Jacobian matrix. If all eigenvalues have modulus less than 1, then the fixed point's stable. If one eigenvalue has modulus greater than 1, the fixed point's unstable. However, the map is non-differentiable at the origin. So we can't use the Jacobian matrix. The Jacobian matrix is undefined. So the question of stability is non-trivial, but it's a fairly basic fundamental problem. I thought it had been solved a long time ago. Only recently I realized there's more to be said. Okay, so what we really want is, in our 4-dimensional parameter space, we want to know for what subset is the origin stable. I don't want to attempt a 4-dimensional picture, makes my brain hurt. So I'll just fix 2 of the parameters and let the other 2 parameters vary. And I'm interested in what set in this plane is the origin stable. Okay, so from the numbers I've given, it's not unreasonable for you to guess that region of stability will be the empty set. But because these numbers, delta L and delta R, these are the determinants of these 2 matrices. I've chosen numbers that are both greater than 1 in absolute value, which means each piece of the map is area expanding. However, I've chosen 1 value positive, 1 value negative. So the map is non-invertible. The map sort of folds. So what happens is the left-hand plane, the left half plane and the right half plane both map onto the upper half plane. Okay, so what do we think the region of stability looks like? Well, I would think it'd be some nice connected region with a few smooth boundaries. So each boundary of the stability region would be a bifurcation. where the origin loses stability in some particular way. So here's what the region of stability actually looks like. And it's incredibly complicated. I mean, there's this nice vertical boundary on the right. This is where the eigenvalues of the 2x2 matrix on the left change from being complex valued to real valued. But then we've got these kind of jaggedy bits down here. But this is not numerical error. The stability region sort of actually looks like this. Okay, so as an example, we'll choose parameters at this point, and ignore the picture on the left for the moment. The picture on the right shows phase space for those parameters. So what's happening is, for any initial point, when I iterate the map, I get trapped in this grey region. So this grey region is defined as, so that this angled line is the image of the positive x-axis. Right. And once iterates are in this grey region, they sort of bounce around in a complicated way, but they always converge to the origin. Okay, so how can we understand this? Well, if we go back to our equations, you'll notice the following. So, 2x. So this is an arbitrary point xy. So let's look at f of 2x and 2y. So we just double the point out to here. Put it in, and you'll see that the 2 just factors out. So this is 2 f of xy. So out to, where's that here? Oops. And of course the number 2 isn't important. This works for any positive number. So what's happening with the map is that any point on this line mapped to a point on this line. So that the angle that I undergo is independent to the length of the point. So if I call this initial angle theta from there to, I can look at the resulting angle, call that some function g of theta. So the map is nice in that I can describe the map. I can describe the rotation effectively with just a single one-dimensional map g. And then I also need a second function, which I'm going to call d, that describes the expansion. So how does this length increase to this length or decrease? Okay, so in blue, this is the map G, describes the rotation. For this example, it's a unimodal map. And then the expansion, that's the red curve, that's the function d. So you'll see that for some values, d is bigger than 1. The horizontal line's d equals 1. So for some values, it's bigger than 1. So the point steps outwards. And for other angles, d is less than 1. So we're stepping inwards. Okay, so instead of iterating the map f, what we can do is iterate the one-dimensional map g, and as we go along, we can evaluate a d that gives us the degree of expansion. And so what we really want to do is we want the average value of d over the lifetime of the orbit, if you like. So as we iterate the map G, we get some sort of probability distribution for the angles theta. Formally, that's described by an invariant measure. And so here I'm showing you the probability density function that corresponding to the measure for this example. And if you average d over this measure, it turns out to be a value less than 1, from which you can conclude that iterates will step into the origin. In a moment, I'm actually going to look at log d and see if that's negative or positive. Okay, so algebraically, this is what we've done, that this works for n-dimensional maps, not just 2-dimensional maps. That the key property is the map needs to be linearly homogeneous, and then we can decouple it into a rotation and an expansion. And I'll skip the derivation. So at the very bottom here, this integral, this is the average value of log d over the invariant measure, mu. And from this formula, we can see that if the average value of log d is negative, then the length of the nth iterate, that has to go to 0. So it means that iterates converge to the origin. Alternatively, if this average is bigger than 0, then orbits will diverge. Cool. Okay, so this sort of framework was all done by a Korean group about 10 years ago. And pretty much immediately, you can state this result. So I should clarify that it's very rare for all initial points to go to the same invariant measure. It's much more likely. It's more likely that almost all initial points will go to some measure. So that's what I'm saying here, that the basin of mu has full measure. So as long as the average value of log d is negative, then iterates converge to the origin for almost all initial points. Okay, so this is nice, but unfortunately it tells us nothing about the stability of the origin, because it only tells us about almost all points. It doesn't tell us about all points. So that might seem a bit nitpicky, but it's important. So let's instead choose parameter values here. So I'm outside the stability region, so according to this picture, the origin is unstable with these parameter values. So here's the equivalent sketch of phase space. So what's happening here, if I choose an initial point at random, but with probability 1, iterates are going to enter the grey region, and then they'll converge to the origin. However, if I choose my initial point exactly on this dashed line, then I'll step over to this dashed line, and then to the middle dashed line, and then on the third step, I'll go back to this dashed line, but I'll have gone outwards just a little bit. And then if I keep iterating, I'll just do the same sort of a period 3 thing, but I'm diverging. And I can choose my initial point as close to the origin as I want, and so therefore the origin is unstable. Okay, so in the context of G and D, so the map G has an invariant measure. Almost all points go to that measure. Here's what the density looks like. And the average value of log D is negative, so things go in. However, the map G also has a period 3 solution. And when you average log D over the period 3 solution, you get something positive, so therefore divergence. Yeah. Okay, so I was able to show that if the average value of log D is negative for every ergodic probability measure, then you can replace the almost all with all. So ergodic measures, I should say, are the ones that can't be decomposed into sort of sub-invariant measures. They're kind of the building blocks of the measures. So this kind of tells us why the stability region is so ridiculously complicated. So each each smooth part of the boundary corresponds to where average value of log d is 0 for one particular measure mu. And the map G is a unimodal map. Unimodal maps can have lots, certainly infinitely many ergodic measures, so lots of opportunity for different boundaries. Yeah. Okay, so what you might be wondering is how did I actually compute this diagram? Well, I put a mesh on parameter space, and then for each point in the mesh, I have some algorithm that determines if the origin is stable or not. So for each point, what I didn't do is I didn't iterate a random initial point, because that would sort of spuriously give this point as being stable. Also, what I didn't do is I didn't evaluate this integral for every ergodic measure, because there's just far too many measures to evaluate. This is not a very practical theorem. So instead, it turns out that there's a very lovely paper from 1992 by Laura Gardini. She is an Italian mathematician working in an economics department, and she did a detailed analysis of a particular mathematical model of macroeconomics, and her model was just a piecewise linear map. And if you do a coordinate change, you can change her map into exactly the map that I'm looking at. And so here's her theorem, just rewritten in terms of my map, if you like. So what we do is we start off with a triangle delta naught, it is, and we iterate it under the map F to get delta 1, and iterate it again, delta 2, and so on. And then we take the union of these deltas from I0 to n. If we can find a number m such that f of omega m is in omega n, so omega m maps inside itself, if we can do that, then we can say that the origin is stable. There's an extra condition that gives us asymptotic stability, which is nice. But the point is that this is something that I can implement numerically, because that the image of a polygon under a piecewise linear map is another polygon. So these things are just polygons. I can encode polygons in my computer with a sort of finite set of points, and I can ask MATLAB to search for m that satisfies this condition, and then draw a dot if it finds such an m. And that's the picture I get. Here I've colored the region by the value of m that it gives me. So this is m is 2, m is 3, m is 4, 5, and so on. Yeah. Okay. One criticism you may have of all this is that I'm kind of looking at a special case. My fixed point just happens to be exactly on the switching manifold. So what I'm doing is I'm looking at a border collision bifurcation. And kind of rule one of bifurcation theory is you don't want to be looking at a bifurcation. You're interested in the dynamics sort of nearby. So I should really have a constant term also in my map. So what I'm going to do now is I'm going to kind of add in a constant term, which is going to perturb my map. And this result says that if the origin is an asymptotically stable fixed point, then when I perturb the map, the fixed point sort of persists as some attracting set. That it'll be a local attracting set. The attracting set could be just a stable fixed point, or it could be some horrible chaotic attractor. All I know is I'm guaranteed to have some attracting set. Okay, so let's see this result in action, if you like. So here's So a toy model of a stick-slip friction oscillator. So stick-slip friction occurs in many mechanical systems related to complicated dynamics in mechanical systems. So one way of trying to get an idea as to why stick-slip friction is causing complicated dynamics is to write down what's the simplest possible system that has stick-slip friction and complicated dynamics. And the idea is if we can understand this kind of system in detail, then hopefully we can learn something about our engineering problems that we actually care about. Okay, so here I've got a linear oscillator, just a mass on a spring, a block, a spring and a damper. And we assume that the block is resting on a rotating belt, and the block has friction with the belt. Sometimes the block is sort of stuck to the belt due to static friction, and sometimes the block is slipping along the belt with some kinetic friction. But the stick-slip behavior makes it a piecewise smooth dynamical system. And so here's the simplest model you could write down. Here you've got a discontinuous function. Yeah. Okay, so this system regularly exhibits oscillations, and then to understand the oscillations, but we do our usual thing of putting in a Poincare section and deriving a Poincare map, and then looking at the dynamics of the map. So a fixed point in the map would correspond to an oscillation of a limit cycle in this system. Okay, so for certain parameter values, this is what the map gives you. You have to be near a so-called Grazing-sliding bifurcation. I won't say what those are now, but they were in the summer school. You'll know all about them. So from the parameters of the oscillator, which sort of all compresses down, we just get two independent parameters, alpha and beta, and so the alpha and beta go in there. I've got my constant term in both maps. The parameter nu is the size of the constant term. Normally I'd use the symbol mu here, but I'm already using mu for my measure, so I have to use nu instead. Okay. Yeah, so this was set up by Robert Sally, Henke Oesinger, and this is the picture they came up with. I've just reproduced it with my own numerics. So this is a numerical simulation indicating what the dynamics are. So I've got the parameter alpha on the horizontal axis, parameter beta on the vertical axis. So the colored regions are where there's a stable periodic solution. So here I've got a stable period 3 solution, here there's a stable period 4 solution, and so on. The black regions are where my algorithm detected an attractor, but one that was not periodic, or period, whatever period I was detecting up to, like period 50 or something. And then finally, the white regions are where there's no attractor. Okay, so while there's all some complicated stuff going on in the middle here, but perhaps from an engineering point of view, you might not be so interested in all this complicated behavior. Maybe you are, maybe you're not, but maybe all you care about is there an attractor or not? And so the answer is that there's no attractor in the white regions, and there is an attractor otherwise. And then we'd like to know kind of why that is. Why are the white regions, why do they look like they do? Okay, so we can use the results, the theorem that I just showed you. So this is for mu negative, so if I put nu, now if I make the value of nu 0, so now the origin is a fixed point, and I can actually determine the stability analytically. So there are three cases. First of all, if alpha is in this range, then the map G has a stable fixed point. So the average value of log D, I'm going to call that lambda. Average value of log D just is log D naught. That's easy. And here's what D naught is. And then I can solve to see whether average value of log D equals 0. So that's the critical case. I can solve to find that this critical case gives me this particular function of beta in terms of alpha. And then case number 2, if alpha is in this range, G has stable period 3 solution. This is the average value of log D equals 0 when beta is this particular function. And then thirdly, alpha is in this range, G has a stable period 2 solution and gives me this function beta of alpha. And so in orange, if you can see that, okay, here I plotted the three functions. There's the first one here, the second one down and up, and then the third one down there. Yeah, so I think this is really nice. It gives a very good approximation to the boundary between where there is an attractor and where there's not. What the theorem tells us is that below these orange curves, there is an attractor. Above the orange curves, the theorem says nothing. And sometimes there is kind of a little strip here where you're above the orange curve, yet there is an attractor. But it's quite a narrow region. I think the curve is a good approximation to where stability actually is lost. In fact, the curve matches exactly around here. So I've got a little over 10 minutes left. So that's the first half of my talk that I wanted to get through. I'll just kind of outline the second half of my talk. I can probably get, just to give you the main ideas at least. Okay, so the next thing to do, I'm going to kind of contradict myself here. Now I'm going to suppose that we really are interested in this complicated stuff that's going on here, and I want to explain that. So what's happening is that the colored regions are mode-locking regions where there's a stable periodic solution. But what's interesting is that the boundaries of these regions appear to self-intersect. So I could kind of sketch one of them, maybe the perfectly period 7 one. It's sort of that's a right. Kind of looks like that. So there are these pinch points where the width of the mode-lock region is 0. And these points are called shrinking points. And the structure is particular to piecewise linear maps. So here's an example of a model in economics, just a piecewise linear map, and the mode-locking regions have these have shrinking points. This is integrate and fire with square wave forcing, same kind of thing, and also a DC-DC power converter. Yeah, again we get mode-locking regions with shrinking points. The last two examples, the models are ODEs, and they have two types of switches. Firing is a switch, and this function's discontinuous, which is like a switch. And DC power converter also has two types of switches. So when you write down a Poincare map, or more appropriate here would be a stroboscopic map, you find that the map is piecewise smooth due to the two types of discontinuities occurring at the same time. And in fact, the piecewise smooth map is almost exactly piecewise linear. In the last case, there is some nonlinearity, and for that reason, you can see a little bit of thickness here, that the boundaries don't quite meet at a point because the map's not exactly piecewise linear. Anyway. Okay. So here's kind of where I want to get to. is what I'm going to do is I'm going to do a local analysis about an arbitrary shrinking point. So I'll choose some nice coordinates so that the shrinking point's at the origin. One axis is aligned with one boundary, another axis is aligned with another boundary. And I want to be able to say something about the nearby mode locking regions. Okay, so this all applies to, it sort of works for n-dimensional maps, not just two-dimensional maps. So we've got some matrix AL and another matrix AR and our constant vector B, so the same kind of map that we've already been looking at. Okay, so a usual thing we do with piecewise smooth maps is we encode periodic solution symbolically. So I use words made up of L's and R's for left and right. So for example, this period 3 solution, it's an LLR cycle because it go LLR, left, right. I could also call it an LRL cycle or an RLL cycle if I wanted to. It doesn't matter. Okay, so it's an S cycle where this particular word is S equals LLR. Okay, so as I vary parameters, one point of my periodic solution could collide with the switching manifold, and that's called a border collision bifurcation. And so the boundaries of the mode locking regions are border collision bifurcations. And so at a shrinking point, you've got two boundaries intersecting. So at a shrinking point, you have an S cycle with 2 points on the switching manifold. Okay. So this is a problem I worked on about 10 years ago as part of my PhD research under the supervision of Jim Meese, who's at University of Colorado at Boulder. And we found that in order to understand shrinking points, you have to look at you can't consider all possible words. You have to look at a particular class of words, which we called rotational words. Basically, that these words correspond to just stepping around a circle with some fixed rotation number. But in phase space, you don't have to have an actual circle. That the concept of a circle is just sort of symbolic, which is nice. You don't have to prove that the map actually has an invariant circle. And then this is sort of what we came up with. Each shrinking point is associated with some word S, and then then we showed that it's not that there are two boundaries intersecting. Really, there are 4 distinct bifurcation curves, and we can characterize these 4 curves nicely in terms of the particular word S. Right. Okay, so at a shrinking point, you've got a periodic solution with 2 points on the switching manifold. If you join up these points with line segments, you get a loop, which is a polygon. And what's interesting is that this polygon is invariant. You start at any point on the polygon, iterate the map, you stay on the polygon. And as you choose parameters to move away from the shrinking point, then the polygon breaks up, but it persists as a one-dimensional slow manifold. Right, and so this is where I made some new advances. The thing I didn't realize when I was doing my PhD is that I didn't realize that, you can really use this one-dimensional slow manifold. So as long as all the dynamics is approaching the slow manifold, which it always will be for the mode locking regions, which are inherently stable, then all the calculations kind of reduce down to one dimension, and you can actually prove some things. Okay, so in particular we can find nearby mode locking regions. That's the new result. So first we need we need the rotation numbers of the nearby ones, and this requires the fairy tree, just quickly. Yeah, so the fairy tree is a graph on rational numbers between 0 and 1, and so if, suppose that at the shrinking point corresponds to rotation number 2/5, then I can use this tree to come up with two sequences. Here's one sequence goes down and bottom, and then another sequence from the right. It gives me two sequences of rotation numbers corresponding to two kind of primary sequences of mode locking regions converging to the shrinking point. Right. So what I do is I do my calculations on the one-dimensional slow manifold, and I can actually determine the shape, roughly, of these nearby mode locking regions. And the shape is, in polar coordinates, it's this function where in polar coordinates, a gamma is given by that. So I think this is really interesting. So somehow this peculiar function, gamma, is sort of fundamental to the structure of the mode locking regions. And here's the simplest way I can think of describing this function to you. So consider this equation. You want to solve that there's one solution is simply y equals x. That the other solution to this equation is exactly the function that I just showed you. Gamma. That's like that. Okay, and then if I go back, there's also shrinking points on the nearby mode locking regions. I can find those. I've got some horrible formulas for when they exist, and I've got formulas for the angles at which they occur. But it's all, it's all formulas that are explicit, and so I can evaluate them in MATLAB easily enough. So just to finish, we'll look at a three-dimensional example, just to show you things don't work just in 2 dimensions. That the result works in any number of dimensions. So we take 3 dimensions, and so here's my numerics. So that this is what the mode locking regions actually look like. So this picture took a long time to compute because I'm numerically continuing the bifurcation boundaries. I'm doing some numerical stepping along, and at each time I'm doing a root finding method to find the curve, and there's lots of different bifurcations I've got to follow. On the other hand, I can just use the 2 theorems I showed you to very quickly give a rough idea as to what this picture should look like. And so here's what you get using the theorem. It doesn't give us the thickness of the mode locked regions, but it gives us the right shape. So, for example, very close to the shrinking point, it matches up quite nicely. This is the theorem, and then this is the actual numerics. But you can see some discrepancies as you get further away. So actually, there's a shrinking point up here, but the theorem, which is just a leading order approximation, the theorem gives you something else instead. Okay. I think that's a good place to stop. So thank you.
Questions?
But a slow manifold, or possibly a center manifold. So if you think about a 2-dimensional map, like I've got here, I can have a 1-dimensional manifold. So I've got some manifold, and the idea is that as I iterate the map, I'm converging to this manifold. So all nearby points get very close to this manifold, and in order to understand the long time behavior, it suffices to consider what's happening on the manifold. And so I can reduce my calculations from 2 dimensions down to just 1 dimension. That's the idea.
You have the word fractal in your title.
Yes.
You showed us some pictures.
Yes.
Where Did you calculate the fractal dimensions
No.
of any of those?
No, it's possibly a bit cheeky to put the word fractal in my title. I haven't proved that I have fractals. Just sort of by intuition, they kind of seem fractal in nature. I certainly haven't computed fractal dimensions.
I mean, just as a low-level numerical thing, you don't know.
Right.
I'm not playing mathematician now. I mean, you can do box counting or something.
I suppose you could.
I mean, it might even be multifractal.
I don't know. I don't have a feel for how good it was, how difficult it would be, but certainly.
Not too difficult. You could solve it before you leave Bangalore.
I can't promise that.
Yeah. Any other questions?
Yes, they can. So here's my parameter space. I've got one parameter on one axis, another parameter, and so this is a special point. It's a codimension 2 point.
I have a question. Could you please give some example of application of border collision bifurcation?
Just from what I've got here, there we go. I claim these are 3 applications. So
Okay.
from economics, from neurons, and also in power converters. Does that answer your question?
This, yes, but it's this some kind of. Can you draw bifurcation diagram? It's some kind of.
Oh, sure. Yes. So I suppose.
It's for physicists, it's easy to understand on this language.
Yeah. So really, each of these pictures kind of shows you what's happening on one side of the bifurcation, if you like. So if I choose parameter values in here, where there's period 5, so that there's really another parameter that I'm not showing you. And so the idea is I've got some stable fixed point, and then at the bifurcation parameter, it turns into a period 5 solution. 1, 2, 3, 4, 5.
So this is really very. It's not smooth. It's not smooth, and no critical phenomena appear around this point. This is what I guess.
Right. It's a distinctly non-smooth type of bifurcation.
Yes.
Smooth maps, so they can't do that.
Let's thank both the speakers in this session and then break for coffee.